Hello, I'm Scott Jenkins, Senior Editor at Chemical Engineering Magazine. Welcome to today's webinar on the basics of temperature calibration. Misconceptions surrounding temperature sensors remain common in the chemical process industries. To help us clear up some of those misunderstandings and to demonstrate calibration methods, we have subject matter experts Roy Tomalino and Ned Espy of Beamex. But before I introduce the speakers, I need to point out a few housekeeping items. The sponsor, the speakers, and the host would like today's event to be more of a conversation, so we invite your participation. As you can hopefully see, we're using video in today's webinar so you can see the speakers and also watch the demonstration, as well as view the slides. There's going to be a couple of poll questions during today's webinar, so when we get to those, we encourage you to respond using the polls tab in your GoToWebinar control panel. There's also going to be a question and answer session toward the end of the webinar, and all attendees are invited to submit typed questions at any point. To do that, type it into the questions tab in the GoToWebinar control panel. All the submitted questions will be captured, and even if we don't have time to get to all the questions, the presenters will follow up with you after the event. You can also contact the presenters directly. We'll put their contact information up at the end of the webinar. If you have a need for technical support, please use the chat tab on the GoToWebinar panel. Don't use the chat box to submit content-related questions. Questions about the webinar should go into questions. Anything for technical support should go into chat. And last thing is, at the end of today's program, a survey should pop up in your web browser where you can provide feedback about today's webinar. So our first speaker today will be Roy Tomalino. Roy's been teaching calibration management for 2 decades. Throughout his career, he's taught on 4 different continents to people from over 40 countries. His previous roles include technical marketing engineer and worldwide trainer for Hewlett-Packard and application engineer with Honeywell. Now, Roy is responsible for all Beamex training activities in North America. We're also going to be hearing from Ned Espy, Technical Director at Beamex. Ned's been promoting calibration management with Beamex for over 20 years. He's helped develop best practices for calibration with a focus on temperature and multivariable instruments. He's a consistent editorial contributor to leading industry publications and has received significant recognition within the automation industry. Currently, Ned teaches calibration best practices and provides technical support to end users and also to the Beamex sales team in North America. So with that, I'm going to hand off the program to Roy. Roy, please go ahead.
Oh, thank you, Scott. So we've got a video coming up on ACE, our annual calibration exchange, and September 16th and 17th. Make sure your computer audio is up for this. Ned, can you get this rolling?
It's that time again. ACE, the annual calibration exchange brought to you by Beamex. And we've heard you, so we're coming back. Back to NASA in Houston. This event features interactive hands-on learning, industry experts where you get to drive the content based on our Q&A sessions. We'll cover the latest trends in calibration, including digitalization. And that doesn't just mean going paperless. There's an entirely different dimension to this that we want to share with you. So whether you're a small instrument shop or you have sites around the world, this event will meet you where you are. Join us.
Very good. So that is September 16th and 17th, and that will be at NASA in Houston, a focus on calibration and live labs, and specifically multivariable transmitters. We'll be doing an actual lab with that. Ned, what's our agenda look like today? Perfect. So Today, we'll be talking about temperature terminology, and not so much for you, but for me. I have trouble with a lot of these big words, so Ned has to break them down for me. So we'll be discussing that, some calibration basics, advantages and disadvantages of dry blocks versus a temperature bath. And if you don't know what the difference is, we'll cover that. Best practices, look at efficiency, accuracy requirements, and, well, logistics. Ned will be doing a live demo, and that's what I am waiting for. A live demo with a temperature dry block and a calibrator, testing a temperature probe and what that looks like. And finally, what our conclusions and takeaways are for that. So Ned, can you let us in on what exactly you're doing? I think you're muted.
Thank you, Roy. Glad to be here. To kick things off, we thought we'd ask everybody a question. So it's not just us talking. We just want to know of all the attendees we have today, how many of you are using a dry block calibrator in your repertoire for calibration? It's a pretty simple question. Just let us, we want to get a feel for what you guys are doing out there. And it looks like slightly more than half out there are not using a dry block, so that's interesting. We'll keep that in mind as we move forward here. So we appreciate that feedback. Roy, you got any comments before we move on?
I know it's surprising, but no, I don't.
Okay, very good. All right, so let's get started. And let's get Roy educated here. So one concept we want to talk about today is the term lag. And it is kind of funny. I checked this on the web, and it seems to be a very big concern for gamers. So we're not talking about that kind of lag today. But
okay, because otherwise you had my interest right there, because lag to me means latency and ping. And when I click a button, I want it to actually be received quickly.
Right. And temperature is pretty much the opposite of a gamer. A gamer is wanting high speed, and temperature moves a lot slower. So, depending on the sensor size, it will react to a step change in temperature slower if there's more mass or it's just bigger. So like a 1/4 inch diameter probe versus say a 1/8 inch diameter probe is going to be much slower to react to a temperature. And of course, how close is the sensor to the heat source? So when you're in a dry block, it's inside an insert, and it's drilled down to the bottom, but it's not as close to the insert as, say, the internal reference sensor. Also, we want to talk a little bit about reference sensors. There's all kind of options. You're going to hear us talk about the internal reference sensor, an external probe. Basically, with external probes, you can get more accuracy. And it's important to note, this is kind of a law of metrology, that the more accurate a device is, the more it costs. This is a picture of a reference probe. And notice it's in a case. You want to take care of these probes. If you were to drop this on the floor, it could cause a significant error and really make the probe useless, or you'd have to have it recalibrated.
One note on that, Ned, I had a very high-end metrologist tell me that even with a probe like this, that you never, when you're inserting it into the block, that you don't ever let it go and let it drop down and hit the bottom. You place it down.
Right.
You could injure the probe and affect your readings.
Yeah, and it's not a stick shift. You want to gently pull it out. So yeah, TLC is is a good term for reference probes. Take good care of them. Also, whether it's a bath or a dry block, there's a control logarithm going on, and everybody's using PID, proportional integral derivative style control. And over on the right is a sort of a step change where you're going from one temperature to another, and you can using PID parameters, you can have an aggressive type control where you overshoot but then come right back in and have this sine wave, or the red line's a more conservative approach where you approach the temperature. So typically with a dry block, you want your sensors to ramp up and approach the temperature. You're not wanting to necessarily overshoot. And then finally, we want to talk about drift, since we're talking about calibration. And how do sensors drift? And so typically, it's normal to see a zero shift. And this is due to the sensor experiencing some kind of shock, or when it gets extremely high temperatures, or if it's in a pipe, if there's fluid going by, it could get bumped around, and it's going to cause most likely a zero shift. So here's a graph. I know it's hard to see, but basically this probe with a tolerance of 3 degrees is somewhere around 2 degrees high, but it's 2 degrees high across the range of, this is a very narrow range, but this is very typical of what you might see on a probe. So the good news is this is repeatable, and you can do things in your control room to bring this back to a true temperature. But obviously at some point, if it's drifted way out, you may want to consider replacing it. So those are what we're going to focus on today. So now let's move on to the differences between a dry block and a bath. So we're showing a Beamex dry block here, and then we're also showing some Fluke products, and both have their place in the industrial world. In general, dry blocks can be smaller. They can even be small enough to hold in your hand. Therefore, they're more portable, and typically they're faster in terms of performing step changes in temperature. And you are going to have an extension cord if you take it out in the field, but it is designed to go into the field. A temperature bath, while it's slower, it takes longer to get the media, typically silicone oil, to heat up. It does provide much better stability and uniformity. So, when you insert a probe into a dry block, the temperature is not the same at the top as it is down at the bottom, and that you want the probe to be down at the bottom in a dry block. With a bath, you can put the sensor up high, put it in the middle. It can be any kind of size, so there is a lot of flexibility there. And if you're looking for the best accuracy on a measurement, it's really the best way to go. So both have their place. But today we're going to be demonstrating a dry block to you guys. And then finally, this is our last slide before the demo. We want to talk about some best practices. And this is kind of my #1 rule for a best practice on anything that you do, is try to use common sense. A lot of people are used to checking something 0 to 500 degrees, or just some kind of range that's going into your control room. But if your process never goes to 0, it never goes to 500, you should, when you're using a dry block or bath, you should have your endpoints represent what the process is in reality. I like to do 3 points where the midpoint would be representative of your process, and then And then just know if you're going below freezing, it takes a longer time to get there, whether it's a bath or a dry block. It can really slow you down if you're trying to do freezing temperatures, which if you have to do them, you have to do them. So here's a typical graph where we're checking it. It's the same graph I showed before, but it's a check at 310, 330, and I can't see the end here, and then 350. So, you know, the reality is you might have a transmitter that's transmitting, you know, 300 to 400, or it could be 0 to 500, but this is representative of your process. So that's the idea here. Another thing I like to push when you're talking about calibration is I feel like your tolerance should be plus or minus so many degrees. You know, whether you're working in C or F at your facility, to me, percent of span doesn't really apply. I want to be within a half a degree C, or I want to be within 2 degrees. It just seems to make much more sense to me to have a conversation about how accurate is my process. Well, I'm pretty confident it's accurate to within 2 degrees when we're making something, whatever it is. Obviously, if it's a reaction or a sterilization, you want to have a really tight number. And again, you know, you want to be within a quarter of a degree or a tenth of a degree. That just makes much more sense to me than a sort of a percent of span number. Also, in best practices, you know, people disconnect the RTD, simulate resistance into a transmitter, and check the 4 to 20. You're leaving out the most important component in the temperature measurement. So we like to encourage people to consider doing loop testing. Loop testing takes more time, but if you're doing an end-to-end test where you're dropping the sensor into a dry block or bath and then checking the readout in the control room, that's to me the best way to check a temperature, because you're making decisions in the control room based on that readout, and you want a true temperature displayed in the control room. Doesn't matter what's going on in between. And then finally, when people design a plant, many times they overlook utilizing techniques that make calibration easier. Many times in furnaces, this is a tank, but in a furnace, you might have a thermal well that's in parallel to the temperature sensor, and you can make a spot check. So you're checking, you want to be in close proximity to the field measurement probe, and you know, you can do that if you put a thermal well in there. In this drawing, if you see the temperature transmitter on the side, if this is 10 feet off the ground, if these legs are really up in the air, you know, how do you get up there with your dry block? Do you have enough cabling to pull this down to the floor? I've also seen installations where the temperature transmitter is mounted up inside the bottom of the tank, and then if you only have a few feet in here, you know, you have to shimmy in there on your back, again, pull the probe out, and then you have to pull the dry block up underneath here to get it into the dry block to make a test. So so try to consider logistics and how can you make things easier. These are things that you can change over time. You know, it might be expensive to add a thermal well, but you can do it when the process is down, and then it's going to save you time down the road. So I think that's enough talking,
Can I ask a
Roy.
question here?
Yes, sir.
So this goes back to the top of your slide. So the use common sense that you put that in for me, didn't you? That's kind of rude because this is in front of a lot of people. One thing I wanted to mention is your example here. The transmitter, let's say, was 0 to 500 degrees. And we get this question a lot. What test points do I calibrate? And your example here is, okay, the process is right around 330 degrees, and you have 3 points from 310 to 350. So this is a perfect example of calibrate what's important to you. And if you had to find a temperature source that would work from 0 to 500 C, that would be extremely difficult. And you don't need to have that. If you have this, you can calibrate what's appropriate for your test to test your process. So I just wanted to point that out. I really liked that example.
Yeah, and you know, if it was 0 to 500 C, it takes a long time for that poor dry block to get down to 0, or it takes 2 dry blocks to make this kind of signal. But if your process never goes there, why bother?
Yes.
So yeah, that's and it's people get into arguments over this, but it really comes back to, well, let's just try to be practical, and people need to understand what does it cost you in time to do stuff that doesn't reflect reality.
Yes. Well said.
All right, so so I guess let's see what happens next. Oh, it's time to have a demo. Are we on time? Let me check here. Oh, we're right on time. Scary.
All right.
So we're going to do a demonstration here with a temperature probe going from 50. So we are going to go below ambient temperature. We're not going down to freezing, and we're going to work in Fahrenheit since we're here in the United States. Sorry about that. But we're going to do 3 points, 50, 100, 150, and we are going to utilize a reference probe. Let me show you, let me give you a little tour here. Here's our dry block in here in my office here, and I'm in a bunker in Hog Mountain, Georgia. And let me give you a little tour here. If we look at the top of the well, I've got the silver area is my insert. This is a probe that I bought from Grainger for about 85 bucks. And here is our reference probe. So this has traceability and gives us accuracy to about, I think it's 0.4 or 0.04 degrees C. I forget the exact number, but it has a little transition here. And we're able to put the Callendar Van Dusen coefficients for this probe into the calibrator, and that's how we achieve the good accuracy with this reference probe. And this is just a standard 385 100 ohm platinum 3-wire transmitter. In fact, if I scroll down here, you can see the terminals on the front of the calibrator. So this is my reference probe. It has a LEMO connection, and it's actually a 4-wire connection. And as I said, it's getting corrected with a coefficient.
Wait. Is this a dry block or is this a calibrator? Make up my mind.
Well, it's this is our new model that has combined our field calibrator, which has all these terminals for doing milliamps and frequency and other parameters. But we've added an extra temperature connection, and then put in the dry block behind it. So it's really a calibrator. We call it a temperature calibrator, but it also can do pressure and your electrical control signal.
Oh, okay.
And it's nice, it has the LCD screen. I know it's not easy to see here, but I'm going to move on here and show, I can show the screen right here. So this is a live display of the screen that's now behind this picture. And let's turn this guy off. And so I'm going to just pretend, I hope you can see my mouse. I'm going to pretend that I'm a technician, and we have all these different functions that we can do. We can do communication, or I can just use it as a standalone temperature, play around with it, change the temperatures or whatever. But I'm going to go right into the documenting mode. And I've got a route that I've set up on this guy. Come on, there it goes. And so today I want to check temperature element 151, and I put IPRT since it has the reference probe in there just to remind me. But the MC6 tells you where to connect. So my reference probe is hooked up to that LEMO connection that you saw, and then I can have a 2, 3, or 4-wire connection here for my field probe. And there's my range. There's my identifier on the temperature probe that I'm using, so it uses the right coefficients. And I'm just going to do a 3-point check. So I'm going to hit the go button here, and I don't think you can hear it, but the dry block's been sitting here at ambient. So let's take a time mark here. It's 26 after the hour, and it's driving down to 50 degrees. So it's trying to move to this window down here. And then already you can see it's off the grid here a little bit, but my reference probe is at 71 degrees, and my field probe, which is a 1/4 inch diameter, slightly larger, it still thinks it's closer to 72. And one of our gurus at our factory, his name's Tony, he makes the point that a temperature probe just measures itself. So, so you have to give, especially 2 different probes, some time to reach equilibrium to what the true temperature is. And a cool feature on our calibrator, I'm going to hit start here so it'll get in the automatic mode. And it is telling us the target here is 50. But I can tap here and we have a graph. So
What?
Yeah, a graph.
How do you tell what the blue line is? I'm confused.
Well, if I click here, it's telling me the blue line is a set point, Roy.
Oh.
And then the red line would be the reference probe, and then the purple line is the field probe. So in this case, the internal reference, so it's graphing 3 temperatures. The internal reference is at 59, but my probes are still up in the 60s, so 2 or 3 degrees apart. But they're trying to get down to the target of 50 degrees. So this is the concept of lag. So if I go back here, this purple line is 1/4 inch. This guy is like 1/8 of an inch. So the reference probe can measure or detect the temperature change faster, if you will. Okay. And then the internal reference, the blue line, it's closest to the heat source. So that's why you're seeing it ahead of the other 2. So that's kind of interesting. Now, let's see. And then, you know, this is my reference sensor, and it is more accurate than the blue line. So we have an internal and an external reference going on. So the blue line is traceable to national standards, as is the red line. But, you know, one thing to note is if you can use the internal reference for your calibration, it makes life much easier for the technician. So that kind of gets back to the tolerance, which is on the next slide.
Excellent point.
You know, by making a really tight tolerance, that's forcing you to spend more money on a reference probe and more care. As I said, a lot of TLC needs to be, you know, some training needs to go on with that. So, you know, set a realistic tolerance. Don't set a tight tolerance or something that's not achievable. You're just making life more difficult, or you need to get a bath, you know, if you're wanting a really super accurate temperature, especially if you have some odd size probes or something. Now, another thing that's going on this graph, so you can see they're starting to get a little closer. We've been at it for 4 minutes now, but it's still not ready to make a measurement. And this is the point where freezing, or we're going towards freezing. So it takes more time to get to a lower temperature than it does to go up. So this discussion is going to last up to 10 minutes here till we see this thing, till these guys come together. But I also want to mention that Beamex is also calculating a stability factor. So the internal reference has just now appeared. It's not very stable compared to the field probe and the reference probe that are in the insert. So they're just kind of trucking along, trying to catch up. But the stability factor, you see it says 2 sigma. So we're calculating the standard deviation over the last minute. And then we double that calculation to give you a stability factor. So this is essentially degrees F. So we're saying that our stability is better than 0.2 degrees F with the field probes, but our internal reference is not very stable at this point. But we don't really care, since we have the red reference probe. That's what we're going to be logging as our traceable temperature. But this stability is really cool to me, because when you see all the sensors being, right now they're below 0.2, you're pretty close. And when it gets down to 0.1, I mean, we're talking 1/10 of a degree stability with a 95% confidence level. It just gives you a lot more confidence in the measurements you're making with this type of technology. So
And
now
one
you
thing,
can see
this
that
confidence
it's dropped
level,
way down. Yeah, go ahead.
so one thing, as you mentioned, this using stability, and I always think of it as a confidence level. It means that you don't have to worry about a certain time delay. Usually a temperature block will hit a certain temperature and it'll acknowledge it, it'll beep, and you have to put in a settling delay, maybe 3 minutes, 30 seconds, something like that. And so this means you don't have to do that, right?
Exactly. And I mean, look how close it is, but there's still, this is 0%, but it just now recorded. So now in fact, let's go over to this. We'll go back to the calibration screen. So it is, it actually, the sensor is going to fail. It's out by 1/2 degree at 50 degrees. So now we've taken our reading at 0%, and now we're trying to get to 50%, which is 100 degrees in this test. So it's starting to run, and let's go back here. So you can see the internal sensor is way faster on the heat. But that was pretty quick, Roy. We got
Yeah.
there, you know, we've been practicing this, and we turned that stability check off. I think it did speed things up. So you can control when the log takes place. So if you want additional delay, all dry block people allow you to dwell a little bit longer if you want to. But our point is look how stable the sensors were when we took the reading. They were all together at you know, so waiting additional time really wouldn't have gained you anything. So
And part of the point here is that the end goal is for you not to have to babysit this test, that you press start and you walk away.
yeah. But this is pretty, this went from ambient of 72 down to 50 in 7 minutes. Now, if you have an older dry block out there, if you bought something, you know, 10, 15 years ago, this is pretty impressive. But if we had said we want to go to 0C or 32F or even lower, just know that it would have taken a lot. As you could see, it would take longer to get there. So it's just something to understand and consider when you're trying to figure out where do you want to test a sensor. But heating is much faster. We're going to see So we took a reading at 7. We should be taking a reading somewhere around 11 or 12 minutes here. But the same phenomena is going on. The stability is off the chart. It's up at a factor of 10 here, 10 degrees, 2 sigma. And, you know, we want to see these guys come back in, and these numbers are going to come back on the chart when these guys get closer to our 50% mark here. So the internal sensor is already there at 100 degrees, but the field probes are still
Lagging behind.
95. They haven't quite even gotten to the 99 area, but and they're not even on the graph. So this sensor has the zero shift going on. So we're going to ultimately end up on the upper end of the scale here for our tolerance once these guys get a little bit closer. So we'll go back to this graph.
Okay, so the bold lines are the actual measurements going on, and the thin lines are the stability numbers.
Correct. And now we're at a temperature above ambient, or 72 degrees in my office here. But you can see it that they're getting, so it took 7 minutes to chill down, but now we're almost there. In fact, the internal reference is actually overshot a little bit, but now it's trying to come back down. So our PID took it to 0.25 or so, and now the internal's coming back in line. But if we go back to the field probes, they haven't even hit, you know, 100 degrees even yet. But now look how close they are. But you can see how this is moving on the graph, kind of bouncing a little bit. So they're not, it's just not quite stable yet.
Yep.
So this screen on the calibrator is really nice, showing you a lot of extra information.
Can you go back to the other screen?
Yes, sir.
One comment I wanted to make is that I guess I'll call it a misconception. I get this a lot, and that is, I don't need to test temperature probes because they either work or they don't. They're either good or they're bad. And this example is proving the fact that, well, yeah, it's working, but it's not good. There's a half a degree offset in the probe that you're never going to know unless you actually test it. And if your process is important enough, then you actually do need to test it. And if it's not, then you don't.
So how do you adjust it, Roy? Is there like a little screwdriver adjustment?
Oh yeah. So we need to, you take it. Actually, you can't. Yeah, there's no adjustment.
Well, pipeline people just simply would put in this half a degree offset into a flow computer and keep on going. But maybe half a degree is pretty significant. They might make the decision to replace it. So this probe is really marginal. It's showing the error is 0.94, 494, 493. It's kind of jumping around at the third decimal. By the way, have you ever seen the third decimal on a temperature? So pretty accurate stuff here. But the reality is this probe is reading high. What's that impact on your process? So so you're in this case, it's probably it's drifted, but it's a repeatable drift. And by doing an offset isn't so bad if you're trying to be within 1 or 2 degrees overall. But maybe by setting it at half a degree, that's your level that you throw it away. So this guy is really, really marginal. So it actually passed at the midpoint here. It was under the 0.5 threshold. It was just barely above there. But let's look over here again. So look at the stability. It got pretty close here. So it was at about the 12-minute mark, but the the dry block did wait an extra 2 minutes or so because the stability was kind of still moving. And look, so it's recording when the stability's practically zero. And then now we're going to 150. It's the same. We're going to see the same graph, the same trend that we saw going from 50 to 100.
Okay. One comment I wanted to make on making an adjustment on a probe, and this is not an adjustment, but if you have an expensive temperature probe, a nice RPRT that's been shocked or dropped, the crystalline structure could actually be offset, and it could affect your measurement or your reading, and it is possible to resolve that by annealing. And annealing means put it in a heat source that is up to the maximum level, super hot, of that probe, and it'll realign those chemical, the structures, crystalline structure. That's pretty extreme.
Yeah. So if you need to do that, you call Roy. Don't call Ned. So
Don't call me I'll be on the phone just to.
Yeah. But yeah, so there's just a lot in doing something like this, whether you're using a bath or a dry block. You know, you really need to just understand what's going on and what's going on in the background. What is this PID control doing? And you know, here now we've got this stability component in the mix. So you know, but if you understand what's the dynamics of what's going on, the internal is always going to be the fastest response compared to anything else that you place in there, and you've just got to be patient. You know, you can't rush through these tests, and you know, and you don't need to use a dry block for every temperature measurement in your plant. But if you've got special reactions that take place, or you're sterilizing, or you know, it's in a reactor in a chemical plant, those temperatures tend to be very critical, and you know, that's where you need to consider, how can I check that probe? And maybe you just do a single point spot check. You could take our reference probe, put it down in a thermal well, and compare that accurate reading versus what the control room is telling you the sensors are reading. So you know, that may be the best that you can do, is just do what I call a spot check. But
Well, how about this? We're doing a 3-point test. Why not do a 3 up down or a 5 up down?
Because let's see if I move this down. So here's this example. If we did this test 310 to 350 and then came back down, guess where it would land? It would land here, and it would land here. It's very repeatable. So in our example right now that's running, we've got to give it some time to stabilize here, but we're going to have a straight line across the tolerance line. And if we went back down and we weighted that nice stability factor, where it's going to land right on top of it. So doing multiple points just for checking out its accuracy is a waste of time. I mean, you could even consider doing 2 points because
Excellent.
the line is the line. Now, if you're wanting to check a profile of something, you could do there are instances where you might want to do 10% steps, because you're wanting to look at a correction factor across a critical zone of temperature. So one of the things about doing these offsets is even though this is off by half a degree, if you put an offset into the control, you're getting a true temperature. So you can do some really cool things by making these kind of adjustments, especially if you've got zone control. If you've got 6 zones, you want all those zones reporting the same temperature to the control room, so that if it impacts your quality, you could raise the temperature a little bit in zone 1 and drop it in zone 6 where it impacts the quality of your product.
Yep, great point.
So using the dry block, you can do some really cool things because you are getting very close to the true temperature. And you can see now that the stability's kicking in, these guys have slowed down. It's a straight zero shift on this temperature probe. And let's take a look at it. So now our stability has gotten down very, I mean, we really could almost take a reading here. It's dwelling an extra minute or so here. And it's looking, it wants that, looks like the internal reference is starting to come in. When that drops in, it's going to take a reading. So I don't know, Roy, is there anything else we need to show here? I mean, we could, we can save this test, print out a certificate if you want to see the graph, the 3 points, the date it was done, who did the calibration. I think we're going to skip through that.
Sure.
But, we can record it. It's recording these readings for us. And you'd be able to document, here's how this probe's working. As of today, it's reading 1/2 degree high, basically, compared to this nice reference probe measuring out to 3 decimal places.
And regardless of what you're doing, this is an automated test. So however you're doing this, you should be using a system that you can press start and just walk away and let this work on its own.
So it did just record those last readings. My max error occurred there at 0. It was 0.512. It was 102% above the tolerance compared to the tolerance. And here I have Peter Parker as my technician, and I can look at the graph. So there's the data that was just observed by the dry block. So you could be writing this stuff down, recording it however you need to record it. And Roy, what does this mean? Does this mean you were bad? It failed?
Yeah, that means I need remedial technician training if it fails.
So
no.
I know this is one of your pet peeves.
Yeah, it is. So I have this thing where nobody wants to be associated with a failed test. And if there's a failure, they'll cancel out of the test, they'll readjust it, make the tolerance larger, whatever. But the failure is the device under test. That's it. It's not
All right. Well, we're a little behind here. It's time to get to our Q&A session. But before we kick that off, what can we say about what we discussed today? To me, the number one thing is to get educated. Understand what's going on, understand how your tools work, understand how temperature changes over the window that you select. But by getting a better understanding of what's going on, it's going to lead to a high level of confidence. That's the whole point.
And it's okay to make changes as long as you understand the implications. It's okay to change what's going on to use more common sense.
And then obviously you need to apply the appropriate technologies. Consider the bath. If you need something portable, maybe the dry block is the way to go. What's the accuracy you've got to deal with, and then it's not necessary that you use a reference probe, but if you're looking for good accuracy, then that's a way to step up your game. They're not, they vary in price, but if you want to get out to 3 decimal places, you need to get a reference probe. So, and then, getting educated here, this is kind of part of it, but, understand your process and maybe argue with the engineer. Hey, look, our process only goes from here to here. Why are we worried about points outside of that window?
Exactly.
So, try to argue with some common sense, and then consider the logistics. If you got to crawl under something to get to the probe, and then the cable is too short, when you have time, recable it. Get a longer cable so that you can work in a nice way, and put in a thermal well if that's if that's a way to get a good temperature check. think outside the box. What can you do to make your life easier when you're doing calibration and faster? I mean, that's the other things. You want to get the stuff done. All right. So we did want to ask this audience. So we want to see if we moved anybody. Do you think maybe you would consider using a dry block calibrator after what you learned today? So so same question, but let's see if we shifted any minds today. So nothing heavy duty here, but we want to give you time to answer, and then after this we'll open it up for the questions. So I didn't see the answers. Oh, there they are. Whoa. How about that, Roy? That's kind of impressive. So we, so at least we got you thinking about it, and you know, pulling the sensor out of the process isn't scary. It's just something that maybe you have to start doing, and you don't have to do it every cycle. It's maybe a once a year check, or you'll kind of know when your probes, if your process has some questionable data, you might want to run out there and check it. All right, well, that was pretty cool. So I think, oh, we do have a commercial, sorry. You know, we focused on just calibration issues today, but we do have a nice reference guide on more in-depth topics regarding temperature. It's really a nice book. It's 53 pages. So it's not, you know, overwhelming. It's a good read. So you've got a link here. You're welcome to download the ebook, and if you would like a hard copy, we can get you. You know, it's kind of a paperback book, but it is put together with ISA, so it's not just a Beamex book. It's got some really good stuff from ISA experts as well. So with
everyone
that,
will receive that link.
Yeah. So with that, do we have any questions?
All right, thanks guys. Yeah, there's a whole bunch of questions coming in, so we're gonna see which ones we can get to here. Just to start out, and I hope I am interpreting the questions correctly here, but I'll give it my best shot. The first question is, does the reference probe have to be immersed in a liquid medium, or can it be kept in the air?
Well, you're going to put your reference probe in the media, whether it's the insert of a dry block, but if it's a bath, you're going to put it into the liquid so that it's measuring the temperature that you're trying to set in the bath. So if it's a water bath or silicone oil, it belongs in there. I mean, if you have the reference probe up in the air, it's measuring the air temperature. So like you saw in here, it was 72 degrees in my office when we started the calibration. And that's what you're going to read wherever it is. I hope that answers the question.
All right, yeah, let's go to another one here. So if I'm interpreting this correctly, the question is how much temperature range, or how wide of a temperature range can be measured by a dry block calibrator?
Well, that's a good question. So you're going to find there's different technologies for dry blocks. The coldest temperature I know is below 100, minus 100 degrees C. There's a couple manufacturers out there, and it's a unique system. I believe it's helium in an enclosed tank, and the helium is pumped through a vortex nozzle, and the faster you pump the helium through, and it just circulates. So the faster you pump it through that nozzle, the colder it gets. So that's a pretty cool technology, and you'll see minus 100 degrees C or even lower. But then that technology can't heat. It's, you know, it can maybe do a little bit of heat. But so the dry block you saw today, it went down to 50. We're using what's called a Peltier technology. So we're running current around the insert to create a cooling effect. And that's the most common for cooling. So the maximum that the unit you saw today, it can go to like minus 14, right? Or I forget the minus C. Is it minus 10 C, something like that? And then the top range is about 150 C, which is about 300 Fahrenheit. So if you want to cool and measure a high temperature, you can't go above like 300 degrees or so. It depends on the make and model.
Yeah.
And
The
then
issue is you can't get one that'll do everything. You got to pick your range of what's going to work for you. So you might have to buy multiples.
if you want to do higher temperatures, those typically don't have the Peltier and do cooling. So your lowest temperature that you can do with a unit that goes high temperature would be just above ambient, like 30 degrees C or 85 Fahrenheit, something like that. So the model we have goes to about 1200 Fahrenheit. There is a nice model out on the market that's it's really a furnace, but it uses a ceramic insert, and it does temperatures for thermocouples up to I guess 1200 C, which is 2000, 2100 F, something like that. So that's typically the highest you would need to go if you're trying to check a thermocouple. So yeah, that's another variable in the equation of calibration is what technology, even within the dry blocks, that you can use. And baths are limited as well. Baths don't go to very high temperatures. There are sand baths that can get you up to that 600 C, 1200 F type temperature. That's about that max for a bath. But that's a good question.
All right, thanks for that. Next, we're going to go to this one here. So the question is, can you provide some rules of thumb for reasonable tolerance limits for applications that are not regulated, such as chemical processes, labs, or pilot plants that are non-FDA?
Well, there's no easy answer. How would you answer that, Roy?
You know, I would just start at a 1% of span. If you're just looking for a target, start there. And
Well,
how much would a
so
1% of span deviation affect the product that's at the end of this process?
and then I'm gonna push you a little bit. What's that 1% of span equate to in temperature? So at your plant, do you work in C or F? That would be my first question, in general. And then if your typical span is 500 degrees, then 1% is 5 degrees. So in a chemical plant, I would say it's not unreasonable to say, if I'm within 5 degrees, I'm happy on this process. So that I think what Roy just said, that might be your starting place, is a temperature like that. And what I say, since Beamex is into the documentation business, is see what your sensors and technology can do, and you'll know what your tolerance is. Like you saw today, that probe it's an $85 Granger probe. It's off by half a degree. Half a degree is a pretty tight tolerance. So maybe, if I said the tolerance was 1 degree, 2 degrees, or 5 degrees, that probe's just fine. It's off by half a degree, but if it doesn't, cause any quality problems or inefficiency in a boiler or whatever, that temperature, So I would say the answer to the question is it can be anywhere from, I've seen, people want to be within 1/10 of a degree, 1/4 degree. They're using reference probes. all the way up to 10 degrees. I've seen people use a tolerance of 10 degrees. So there is no right answer. As a technician, I would argue for the higher number that I could get, because the higher the number, the easier it makes life for the technician. But the control engineer, they're going to tend to want to say a real tight tolerance, and I would argue with them, don't make it too tight, because now you're making me use a reference sensor that maybe it's not necessary. We're having to buy more accurate equipment, so it just the tighter the tolerance, the more it's going to cost you. You might have to calibrate more often to achieve that tolerance. Like if you say you want to be within a 10th degree, you might have to go out every month to make sure it hasn't drifted by that amount. So it can cost you in a lot of ways if it's tight. So it's somewhere in between.
Yeah, sounds good. All right, so next question. The questioner says, if I want to calibrate an RT or RTD from 0 to 100 degrees C, should I calibrate it from 0 to 100 or from 100 to 0? And which would provide the best results?
I think you would see identical results. What do you think, Roy?
I think it'd be the same results, and I think it just depends which would be faster. And it's my opinion that starting 0 and going up would be faster.
Yeah, just because you're starting at 72, or well, you're starting at 20 degrees ambient, so you only got to chill down to 0. If you start at the high temperature, then you got to chill from 100 down to 0. It would take a lot longer. So yeah, I would recommend the 0 up. And you could use an ice bath. That's 0 degrees C. That takes some time, though, to properly make it. So you saw today we got to 50 C, which is probably, or 50 F, which is what, maybe 10 C or something. We got down there pretty quick, so it wouldn't be maybe 10 minutes max to get down to the 0. So with the dry block technology, you could do that test maybe in 15, 20 minutes. Starting at 0.
All right. Another question, if I am interpreting this right, asking about what the results or how the results might differ if they were using a circulating bath.
Well, compared to what you saw today, a bath would certainly do what we did. It would chill down and it would go up, but I would say it would take at least twice as long, maybe 3 times as long. It's just a lot slower, but depending on the bath, you could put 4 or 5 probes in that bath, and you'd be able. But we've done some calculations, and I think using a dry block, doing separate sensors, you could probably do 4 sensors in the same amount of time as doing 4 in a bath. But with the bath, you're babysitting it and not having to move things around, whereas testing 4 sensors one at a time, is more manual work. But I would say, if you had the same reference probe in the bath, you would pretty much see identical results as what we showed with our dry block today.
All right, sounds good. So we'll go on to the next one here. So another question is, do you think the probe bias will stay similarly constant across a wider range? The questioner asks about, say, a 400 degree Fahrenheit range.
Yeah, well, so bias to me, are you talking, my question would be, is that a slope? Are you seeing a As you go, let's say you go from 350 to 450, is it kind of going uphill or is it kind of going downhill? I would really question that probe. But if you're using the term bias the way I was using it earlier as offset, if it's off by, let's say what you saw today, if it was a half a degree high at 350, you're going to see half a degree high at 450. I mean, to me, that's a normal working sensor. If you're seeing just a zero shift on it, it just follows across the whole capability of the probe. If you're seeing a slope, then that would be another indicator. Maybe it's time to replace the temperature element. But again, if you're hooked up to a transmitter, you could go into the 4 to 20 and take that slope out of it and you could make that 4 to 20 measure, represent the true temperature versus, compared to the dry block. And so again, you can correct a probe if you're seeing repeatability with it, you can get really good results as far as your control is concerned.
Yeah. I just wanted to say that I think that probe that we did had a slope, but it was really marginal or very small.
It's a little uphill. Yeah, I like that probe's off. It's real world. Kind of shows you.
Yeah. So another thing that came up here is whether you could summarize the pros and cons for dry block versus temperature bath.
Well, can you see my slide? I changed it.
Yep.
I mean, you can buy a dry block that you can literally hold in your hand. It's like holding a Bible or something, and they're not very accurate. But if you put the reference probe in there, it gives you, it can work pretty well. If you're working in the shop and not having to carry the bath around, then the bath might suit you if you're looking for good accuracy. I mean, we see baths a lot in pharmaceutical plants where you have the short sensors that use a triclover type clamp. So there's a flange that you have to deal with, and people in pharmaceutical are looking for really good accuracy. But it's called a bath, and even if you put it on a cart, there's a technical term called sloshing. I mean, the media it's hard to keep it from spilling out. But this image in the lower right corner, I mean, this is what Beamex has in our lab, in our temperature lab, and it's super accurate stuff. So we're trying to be more accurate with what we're delivering to the marketplace. So we are using special baths. They're not
So if I could
portable bath.
If I could just make a comment, I think on the bath, normally you're looking at one bath per certain temperature. So if you're dealing with 2 or 3 temperatures, you're taking the probe and you're putting it in each bath and not ramping up the temperature generally. So you could say that the bath is more accurate, it's slower, but you could do short sensors, you could do multiple sensors, and the dry block is cheaper and more portable.
The old technology is a temperature bulb. They're still out there. You can't put that in a dry block. I mean, the only way to check something like that would be with a bath. And there's people that make water baths. You're just trying to be in the ballpark or something. So I mean, there's lots of ways to do it. But
I think it's
But the other thing that I think we demonstrated today with the dry block is the newest dry blocks on the market are very fast. I mean, 5 minutes per point. So I think a lot of people that have been around a while, they're used to 15, 20 minutes a point with a dry block. And the units on the market today are very fast. So, you know, and you also have a lower price point. So it just, you know, I don't have an answer to that question, but I think we've tried to summarize it here. I think these are the main bullets. So give us a call if you need a better answer than that.
Yeah, that's good. So we are coming to the end of our time here, but we think maybe we could squeeze in one more question. There's one here about how often do you need to calibrate a dry block to a national reference standard?
I would say it's once a year. Roy, what do you say?
I would agree. There's going to be a certain uncertainty if you have it calibrated once a year, but if you wait to be 2 years, that uncertainty will grow. Once a year is normal.
I mean, Beamex explicitly specifies a 1-year uncertainty. So our published specification are valid for once a year. But, you know, if you're a water treatment plant and your accuracy is like this 5-degree or 10-degree type tolerance, you've got really good coverage with the internal reference sensor. So why not go 2 years? Or, you know, or maybe see how it does in its first year, and then you could back off the schedule if you're in that kind of situation. On the other hand, if you're kind of paranoid, if you're a nuclear power plant or a pharma plant, maybe you want to check that dry block in 6 months. And if you've noticed that it's pretty stable, pretty reliable, then maybe you go to 9 months the next cycle, and you could work your way out to once a year. And again, it just comes back to, you know, having some confidence. And the only way to have confidence is to analyze and document, you know, how's this instrument performing. So whether it's a probe or whether it's your calibrator, you know, you should look and see. I would say in practice, calibrators drift the most their first year, and then they kind of get pretty repeatable. So once a year is the answer.
All right, good stuff. All right, so we have kind of come to the end of our time here, but I just want to remind everyone that the questions are all captured, so the speakers will take a look at those after and get back to you. If you missed any portion of the webinar, or if you want to watch the recorded version again, you're going to receive an email with the link to the recording and also some additional links that have supporting information, including a PDF version of the slides from today's webinar and some contact information as well. As a reminder, when the webinar ends, there's going to be a survey popping up, including a question about next topics you'd like to see. So if you want to get back to provide some feedback, that would be great. But before we sign off, I just wanted to thank all of you for attending. Thanks to Roy and Ned for all the information and the demonstration. We hope you all learned something here, and definitely hope to see you again in a future webinar. So thanks.
All right, thank you. Take care, everybody. Be safe.